Hi, Mr. Pope here from Grammar School for Boys, and this is the sixth decision video I'm making, and it's going to be on linear programming. So, what is linear programming? Linear programming is essentially we are going to be finding solutions by considering a feasibility. And I always mispronounce. Feasibility region. Okay, so we're going to consider a problem that's got many variables, and we're going to draw this problem in a two-dimensional plane and solve for a feasibility region. Okay, so what do I mean by that? Well, suppose you have a problem with two variables, okay? Then that's okay, because then we can plot them as functions of x's and y's. And we can solve this graphically 2D. That's totally fine. What's going to be coming up next, I'll put a star, is we're going to be looking at a simplex method. And the simplex method deals with problems where there's three or more variables. And the reason we use that method is because drawing 3D, 4D and 5D sketches just isn't particularly useful. Okay, so essentially we're going to be solving problems using 2D sketches. So I'll do a really easy one and a completely abstract case. So suppose I've got my XY coordinate axis like so, and suppose I have the conditions that x has to be greater than 5, y has to be greater than 2, but x plus y has to be less than, let's say 10. Let's say equals 2 there, and that's equals 2. Okay, so what's going on here? Well, this inequality would be represented, as you'd expect, with a vertical line, but dashed because it's a strict inequality, and we want everything greater than 5, so I want that side of the line. Okay, y is greater than 2. If I that colour, then I should have made it clear that that's 5, and then 2 on the y-axis is going to be somewhere there. So because that's greater than or equal to 2, I need to draw a horizontal line that's solid, and I want y is greater than that value. And now consider this green function here, x plus y is less than or equal to 10. Well, it's pretty obvious that when y is 0, x is 10. So 10 is over here. And when x is 0, y is 10. So this looks like it's going to be a sloping down line with gradient 1 like so. It's a solid line because this is a less than or equal to inequality, and I want less than 10, so it's clearly going to be all the points below this line. Can you see that the region, let's say the feasibility region, which is R, is only satisfied in this red triangle here? Okay, so suppose I've got a problem and there's these things here, and these are called constraints. And sometimes the question might ask you to read a bunch of text and then from that figure out your own constraints. And There isn't much to it, you just have to have a little bit of comprehensive skills about you and read. And I've given the example in a completely abstract context, but suppose we're asked to, first of all, sketch the feasibility region. Well, clearly it's this little triangle here. Please note that when it's less than or greater than, we used dashed lines, and then when it's less than or equal to or greater than or equal to, we use solid lines. Okay, takeaway. These are the constraints, and we're going to be solving stuff by considering a two-variable problem of the feasibility region. Now, here's the magic. First of all, we're going to be interested in these vertices, okay? Because we're essentially going to be solving this using the vertex method. And the vertex method is the following. If we wish to maximize an objective function on the feasibility region, then a solution exists either on or near a vertex. Okay, now you're probably thinking, okay, why can't it be on or near? Well, because of the following. Suppose x and y are discrete. For example, they could be tickets, they could be people. The problem might deal with they have to be solutions that are whole numbers. And in this case, what you do is you check integer coordinates near the vertex, but in the feasibility, feasibility region. Okay, and what if x and y were continuous? Then you can just, then you can just go straight to, well, it's just the vertex. The vertex coordinates are the solution. So you've got to be really careful if x's and y's have to be whole numbers, so they're discrete packets, or they're continuous, in which case you can just have the vertices themselves. And this is really important. Okay, you have to do this check. So at the moment, I haven't actually said whether discrete or continuous or not. So, for example, let's give an objective function. So an objective function may be to minimize or maximize, usually p for profit or something, where this profit is a function of x and y. So let's take an example. Let's say I want to maximize p, where that is 2x plus 3y. Okay, so my objective function is usually something like this, and it's a function of both x and y. And let's suppose I want to maximize this for a given objective function, that is p is 2x plus 3y. Okay, what we do is we draw this line first and we pick some number of p. All we're interested in is the gradient. So common trick I do is I say, well, what's the lowest common multiple of 2 and 3? Well, that's 6. So let's say 6 is 2x plus 3y. So I know that when y is 0, x is 3. Let's do this in a dark colour. So let's say 3 there. And I know when x is 0, y is going to be 2. Yes. So my objective function line is going to look something like this. That is terrible. Tell you what, let's draw this like this. Let's give it a twiddle. Okay. Oh, really? Oh, man. Okay, I'm trying to get this objective line so the gradient's roughly right, but it's just not having it for some reason. Mate, it's probably better if I just draw it. Okay, so what I'm going to do... Oh, really? Okay. Apologies for this. Maybe I'm not very good with this software. Okay, so imagine that this is my objective line and it's got a gradient of, well, what's the gradient? It's clearly minus 2/3. Now the idea is you can use a ruler, and for this objective function, if I slide it from left to right while preserving the gradient, look what happens. That vertex is the first one it's going to meet. So when the objective function first touches the feasibility region, that is going to be the minimum. And now as I slide it along, it's in the space, it's in the space. And now notice it's going to touch the bottom right vertex next. And if I keep going, the top left vertex is the last point for which that objective line leaves the feasibility region. So we can conclude that this point here is the maximum. This is the maximum P. And if you want to check that, let's try the vertices. So let's call this vertex 1, this vertex 2, vertex 3. So where's vertex 1? Well, that's clearly the point when x is 5 and y is 2. Now, what's P going to be? P is going to be 2 lots of 5 plus 3 lots of y, which is 2. So 2 5s are 10 plus 3 lots of 2, that's 16. So the second vertex, what have we got here? Well, I know the y coordinate is 2, and now the x coordinate is such that it's on this line. It's on this green line, which is x plus y is less than or equal to 10. So that means x must be 8. So the P function is going to be 2 lots of x, which is 8, plus 3 lots of y, which is 2. So 2 8s is 16, plus 3 lots of 2 is 6. 16 plus 6 is 22. So no surprise, it was bigger. Now let's look at the third vertex. Well, the third vertex is clearly going to be when x is 5, and the y value is going to be 5, because remember, if it's the intersection of this green line and orange line, then it must be the case that x plus y equals to 10 is that point there. So P is going to be 2 lots of x, which is 5, plus 3 lots of y, which is 5. So 2 lots of 5 is 10, plus 3 lots of 5 is 15. 10 plus 15 is 25. So we've actually found the maximum value for P. Okay, and it was the vertex. Now, technically, this P value is a maximum at that vertex, but we can't include that vertex because of this dashed inequality line. So if the lines were solid, we could include the vertex. Okay, now if we can't include the vertex, then we'd have to pick the next available point inside, like so. And for all intents and purposes, because we can pick a point that's infinitely close to that point, then essentially we say, well, okay, put it this way. There's two things that can happen here. If x and y are continuous, right, remember what we mean by continuous, then it's just the vertex that's the maximum. And the reason why the vertex is the maximum here is because I could go to an infinitesimally small point away from that vertex, and it would make an infinitesimally small difference to my p-value. Because I can't technically have the vertex because of this inequality line, but I can move an infinitesimally small distance away that it's essentially the same point. So if it was a continuous case, then yes, the x and y, if they were continuous, then I would just have 25. If x and y were discrete, and I haven't specified here, then what would we have to do? Well, if I was to blow this up, this ring, so imagine we've blown up that ring, and we had the green line going like that, and we had the orange inequality popping down like so. And let's get a few points down. So this point here was the point 5, 5. And by the way, our feasibility region was all this down here. I'm going to be forever if it's that small. Let's have that. Our feasibility region was all of this space. Okay, what we're going to do is we're going to form a little grid. So let's suppose we go down to the next integer. So what was this? This would be 5, 4. Then if we go down to the next one, it's going to be 5, 3, and then 5, 2, and so on and so on. Right. Question. 6, 4, is it on this green line? Yes, it is, because 6 plus 4 equals 10. And that's the whole point of this x plus y is less than or equal to 10 stuff. 5, 3, well, if I go over to here, that's 7, 3. So that means this point here, if I was to draw a grid, would be 6. It would be 6, 3. And then if I just kept on going, so then this would be 5, this would be 6, 2, and then I'd have 7, 2, and then over here I would have 8, 2, and so on and so on. So the question is, we're not allowed this vertex because it's on an inequality line. So we've now got these points here to consider. Those 3 points are nearest to the point in the top left. And we can't include these ones because they're on the inequality line, so we can't have them. Well, it's pretty obvious now that if we're trying to maximize p equals 2x plus 3y, that for the top one, I'm going to have 2 lots of 6, which is 12, plus 3 lots of 4 is another 12, so that's 24. For this one here, I'm just going to have 3 less than that, which is 21. Because I've got 3 lots of 3 is 9, plus 2 lots of 6 is 12. And then over here, the last one we need to check, I've got 2 lots of 7, which is 14, plus 3 lots of 3 is 9, 14 plus 9 is 23. So in actual fact, p, the maximum value of p is 24 when we're taking over the integers. And yeah, that's pretty much this chapter. If you can read, if you can formulate inequality diagrams, if you can understand the idea of an objective function, and to minimize it, you want the bottom left vertex, or as the objective function is going into the feasibility region, and if you want to maximize, it's usually the most top right, or the vertex as the objective function is going out. And now it's not completely obvious which one that is because it depends entirely on the gradient of the objective function. So yeah, please be careful with that. But yeah, that is essentially it. Yeah, so it's just about solving graphical problems, really, and trying to optimize coordinates in a two-dimensional system. Later on, let's have a look. When are we doing simplex? Simplex will be next week, and Simplex is just an algorithm to do the exact same thing. We're going to minimize or maximize problems given conditions, and it's just the 3-dimensional, 4-dimensional, 5-dimensional, as many dimensions as you want. And we use that method because clearly to draw things in 3D and beyond is just going to make things difficult. Okay, essentially, yeah, Simplex is just a simplex is it's an n-dimensional polygon that has the least amount of vertices that span the space. So what do I mean by that? Well, okay, so I only need one node for 0 dimensions. I only need 2 nodes to denote 1 dimension. There it is. I only need 3 nodes. I need to add 1 more node, and now I've made a triangle of some kind, and now this is a 2-dimensional shape. And now, well, you're going to have to put your imagination hats on here. I only need 4 nodes, 1, 2, 3, 4, to create a tetrahedron, a triangular-based pyramid, to make a 3-dimensional shape. And these are all n simplexes, where n is the dimensions that we're needing. So yeah, it's essentially breaking down things into n simplexes and going along the vertices, and each of these vertices are things that the method goes along. And we'll talk about it next week. Right, okay, so, cool. Here's a question for you to have a go on. Pause the video, I'm just going to get a drink, give it a go. Okay. So, the captain of the Mal de Mer takes passengers on trips across the lake in her boat. The number of children is represented by X, and the number of adults is by Y. So clearly X and Y are discrete. So we're looking for integer solutions, right? Because I can't have 2.3 of a kid or 4.5 of an adult. It has to be whole numbers. Okay, 2 of the constraints limiting the number of people she can take on the ship are X is less than 10 and Y is greater than or equal to 2 and less than or equal to 10. These are shown on the graph. So X is less than 10 is clearly this inequality here, and Y is trapped between 2 and 10 are these horizontal ones here and here. Okay, these are shown on the graph in the figure above, but I put it to the left, where the rejected regions are shaded out. Okay, explain why the line x equals 10 is shown as a dotted line. It's because this is a strict inequality, and solutions on this line are not valid. Okay. Use the constraints to write down 2 statements that describe the number of children and the number of adults that can be taken on each ship. Okay, so what is this saying? Well, what does the constraint x is less than 10 mean? Well, essentially, the first one is saying no more than 9 kids allowed on the ship. So win, lose or draw, you can't have 10 or more kids on the ship. And the second constraint is at least 2 adults, but no more than 10 adults are allowed. So you can have anywhere between 2 and 10 adults, but you've got to have less than 10 kids on the ship, 9 kids or less. Okay, for each trip, she charges £2 per child and £3 for adult. She must take at least £24 per trip to cover the costs. The number of children must not exceed twice the number of adults. Okay, so let's put it this way. The number of kids is going to be 2, well, the number of kids is X, so the amount of money that they'll get from kids is going to be 2X, and then there's going to be £3 for adults, that's 3Y, and this has to be at least, so greater than or equal to 24. Okay. The number of children must not exceed twice the number of adults, so that means X has to be less than or equal to 2Y. Does that make sense? The number of kids, X, must not exceed, so must be the same or less than the number of adults, twice the number of adults, i.e. 2 times Y. So here are my two inequalities that I formed. Okay, I'm hoping you can see where I got those from. And a lot of this is just going to be reading and just going, okay, I just need to form some inequalities, and it's just a pretty simple skill, but I mean, if I'll do it a couple of times, you'll get the gist of it. I'm hoping. Anyway, part D. Add 2 lines and shading in diagram 1 in your answer book to represent these inequalities. Hence determine the feasible region and label it R. Okay, so let's get rid of these colours. First of all, let's tackle this X is less than or equal to 2Y. Okay, so if X is less than or equal to 2Y, then Y is greater than or equal to X over 2. So what does the Y, so let's consider, what does the Y equals X over 2 look like? Well, this is going to be a line plus 0. It's going to be Y equals mx plus c, so it's going to be going through the origin as gradient of a half. So that means for every 1 along, I go up a half. So for every 2 along, I go up 1. For every 4 along, I go up 2. So I know there's a point. So up 4, along 4, up another 2. So there's another point. Along 4, up 2. So there's another point, and so on. So I'm going to have a line that looks like this. Something like that. Now, if I get rid of the x's, like so, now I just have to consider for what points, for what side of this inequality do I want? Well, I want 2y to be greater than or equal to x. It's greater than or equal to, so it's a solid line. And now let's just pick a point. Let's say this point here, where x is 0 and y is 4. If that point is true, then all the bits above the line are true. If it's not true, then all the bits below the line are true. So, if x is 0 less than or equal to 2 times 4, which is 8? That is true. So I actually want all the bits above this line, which I'll denote like that. So as far as I'm concerned, this one's done. Next up, I'm going to have a look over here, and I'm going to try and plot this line. Now, you've probably done lots of this in year 9 or year 10, but we can do the cover-up method if you want to. So 2x, if y is 0, is 24, so x must be 12 when it's on the x-axis. So like that, let's give it a different colour, let's say pink. And then let's suppose x is 0, so 3y equals 24, so y is going to equal to 8. So I'll put a little cross in there, like 8, like so. And I'm going to draw a straight line like that, like so. Okay. Now, in actual fact, I should really stick to the convention. They've shaded the bits they don't want on their diagram. So just to not confuse ourselves, I'm going to do the same thing. Although it doesn't particularly matter which way around you do it, to be honest, as long as you've been consistent. So let's think about it. Can I substitute a point to check this easily? Well, yes. Look at the origin. 0, 0. Is 2 lots of 0 plus 3 lots of 0 greater than or equal to 24? No. So if the origin's not cool, then everything below the line is not what we want. Okay, now the reason I didn't use 0, 0 before is because the line was actually on 0, 0. Can you see how the red one is going through it? So substituting 0, 0 in there is not going to have much of an effect. So now, if I want to shade the feasibility region, I'm hoping you can see that the region I want is going to be this. So that, I'll label it R, let's have a more distinct colour. That is my feasibility region. So add 2 lines and shading to diagram 1, done that, hence determine the feasible region, labelled it R, yes, I've done that. Okay, use your graph to determine how many children and adults would be on the trip if the captain takes the minimum number of passengers and the maximum number of passengers. Okay, well, the minimum number of passengers, well, put it this way, the vertices are going to maximise stuff, aren't they? So we're either dealing with this point here, this point there, this point here, this point here, or this point here. But it's important to notice that because this is an inequality, I can't actually use that. So the next point in would be over here, which is 9, 10. And then the next point down would be 9, 9. And I'm not interested in 10, 9 because that's on the line. So that will do. Okay, so vertices wise, any vertices on here will satisfy it. So on the left hand side, we've got x is 0, y is 8. We've got x is 0, y is 10. We've got at the bottom here, what is that? That's interesting. Well, let's say we go 6 along and 4 up. Is that on the line? Yes, I believe it is, because 2 lots of 6, which is 12, plus 3 lots of 4 is another 12 is there. So that vertice will be 6, 4. What about this one, the actual one itself? Well, I don't think that's going to be a vertex, that's going to be an integer, because here's 7, and if I scroll up, here is 7, 4. Well, okay, and down here, this point is 6, 3, and this point here is 7, 3. So the intersection of that pink and red line clearly isn't an integer, so I don't need to worry about it. I mean, if you did want to find out what the coordinates of that integer were, then you would just have to solve simultaneously 2x plus 3y equals 24, and the other one was 2y equals to x. So if x equals to 2y, then 2 lots of x is going to be 4y plus 3y equals to 24. So 7y equals to 24, so y equals 24 over 7. Shock horror, that's not an integer. And x is going to equal double that y, so it'll be 48 over 7. So clearly this is not an integer, so we don't need to worry about it. Little thought bubble. Okay. Next up, we can look at this vertex over here, and I believe this is going to be the nearest integer thing here, which is 9, 5. If I go down to here, that's 9, 4, which is outside it. This value here is 8, 4. Okay. Well, it should be pretty obvious, actually. What's the question asking? Use your graph to determine how many children and adults will be on the trip if the captain takes the minimum number of passengers. Well, clearly, this point is the minimum, because that point there is taking 8y, so 8 adults, 0 kids, is a total of 8 people. And there's no other value that's going to get smaller than that. Okay. What's the maximum going to be? Well, it's going to be somewhere in the top right. The reason why I'm going to pick that one over there is because if I look at all of these ones in the vicinity, 6, 3, well, 6, 3 is not on it, so let's get rid of that. Don't need that anymore. neither 7, 3, then we've got either 6, 4, 7, 4, 8, 4 near that vertex. And clearly 6 and 4 is 10, 7, 4 is 11, 8 and 4 is 12. So they're clearly not smaller than 8. If I look in the top right, 9 and 10, i.e. x is 9, so 9 kids and 10 adults. So 10 adults and 9 kids is the max, so that's 19 people. So if I just take that and plonk that over here, there's my minimums and maximums. So the minimum number of passengers is we take 8 adults and no kids, and the maximum number of passengers is 10 adults and 9 kids. Okay. Technically, it's a bit of a weird question because actually this 2x plus 3y is actually an objective function. And if we took that objective function and slid it up to the right, then we'd still be left with this vertex up here. And technically 10 adults and 9 kids would be the maximum amount of money. So if you're looking for a profit, or total sales rather, the maximum is also going to be 10 adults, which is £30, plus 9 kids, £2 each is 18. So this person's going to make £48 maximally. Yeah, interesting question. But yeah, pretty easy. Okay, so if you want to, pause the video, give this question a try yourself. I'll zoom in a little bit so you can pause it and read it. Essentially you need that diagram. Okay. Keith organises 2 types of children activity, sports mad and circus fun. He needs to determine the number of times each type of activity is to be offered. So again, we've got a discrete case where we must have integer solutions for x and y. We can't have x is 0.2 or something like that. Okay, let x be the number of times he offers the sports mad activity, and let y be the number of times he offers circus fun. The 2 constraints are the follows: x is less than or equal to 15 and y is greater than 6. Okay, explain why y equals 6 is a dotted line. It's because it's a strict inequality and solutions with coordinates of y equals 6 are not allowed. Same reasons before, a bit dry. Okay, 2 further constraints are the follows: 3x is less than or equal to 2y and 5x plus 4y is less than or equal to 80. Add those 2 lines and shading to the diagram above book to represent these. Okay, so we've just got to draw it. So 3x is less than or equal to 2y. Okay, well, what's another way of doing this then? Well, if x was 2, y would be 3. So x is 2, y is 3. So let's whack that point. Well, it's that point there. And when x is 4, y is going to be 6. So 4, 6, like that. So actually, I can just draw a diagonal line through the origin, because this is a y equals mx plus c job. And with a bit of practice, you guys will get a lot quicker at doing this stuff as well. Just making sure it goes through the points. Cool. It's going to be a solid line, and I want the 2 y's being greater than 3 x's. So if I pick this point here where y is 6 and x is 0, clearly 2 lots of 6 is bigger than 3 lots of 0, so I want the bit above that line. So that means I need to shade the above part of this line if we're going to stick with that convention. Technically I should have carried this line up like that. Oh no, that's ruined it. No, it's fine, it's fine. And then 5x plus 4y is less than or equal to 80. So we'll do the cover-up method. So if y is 0, 5 lots of what is 80, I believe that means x is 16. So there. And then if I cover that up, 4 lots of y is 80, so y is 20. So I just draw a line between 20 and 16, like so, like that. And I want that total to be less than or equal to 80, so I want the bit below this line, like so. So I'll shade the bit above it. So in actual fact, what is the only feasibility region? Well, it's actually this triangle here. That's the only bit that satisfies all four constraints. So we'll tie this up with a bow and we'll label it R. Okay, each sports mad activity costs £500. So let's get an objective function going. So 500x, and the circus fun costs £800. So plus £800. Okay, Keith wishes to minimise the total cost. Okay, so if we call this C for the total cost, we want to minimise C. Now, because C is a constant, I can divide by, okay, I can take this objective function, I can scale it down. So essentially this is 5x plus 8y is some new C, let's call it C prime. And if I want to, so this is my objective function, let's not get that twisted. But when it comes to actually plotting this new objective function, to make it easier, I always scale it down. So if 5x plus 8y equals C, what's the common multiple of 5 and 8? That's 40. So let's consider the line 5x plus 8y equals to 40. So when y is 0, 5 lots of what is 40? Well, that's 8. So it's going to cross at 8, 0. And clearly it's going to cross at 0, 5. And I can scale these up. So instead of being 8, I can make it go through 6. Well, no, let's do that. So I've got through 8, and then 0, 5 is about here. Okay, so when it comes to the next part, use your graph to determine the number of times each type of activity should be offered and the total cost. You must show sufficient working to make your method clear. Okay, so this is my objective line here. So I would label this the objective line. And if I want to minimize it, I would technically take this objective line and I would slide it up, and it's clearly going to hit that bottom one first. So really, I need to test the integer solutions in the neighborhood of here. So let's think about that. Where are they? So I can't have this one, which is 4, 6. I can't have that. I can't have 5, 6. Can I have 5, 7? 1, 2.5. I believe 5, 7 is there. Interesting. It looks like 5, 7. We can't have 5, 8 because that's up here. And then clearly if we keep going to the right, so we're here at 6, 6, and if we go up to 6, 7, which is here, then clearly we've increased x and y, so it's going to be at a greater cost. So it looks like x is 5 and y is 7 is what we're going to be dealing with here. So the minimum C is when we're at x is 5 and y is 7, is going to be 500x, which is 500 times 5, plus 800 times y, which is 7. Let me just double check I've done that right. Yeah, 5, 7. 500 times 5 is 2,500, plus 800 times 7 is 5,600. So what's that going to be? Carry the 1. Is that 8,100? Seems legit. So £8,100 is going to be the minimum cost of doing all of these activities. Nice. Okay. So yeah, just be careful. If it's a discrete problem and you have to have integer solutions, you have to check all of the integer solutions in that area. I mean, if you've drawn a nice graph and you've got it like this, then you can just read it off. If you didn't, you'd have to do some simultaneous equations and check which ones are above or below. But this was fairly easy, so I didn't have to do that. Okay, last one. Cool. So pause the video, give it a go. Wait a minute. I'll have this, so pause it when it's like this, and unpause it to get the next bit, and then the last bit. Okay, right. You are in charge of buying new cupboards for a school laboratory. The cupboards are available in two different sizes, standard and large. The maximum budget is $1,800 and standard cupboards cost $150 and larges cost $300. Let X be standards and Y be large. Write down an inequality in terms of X and Y to model the constraint. So, if X is standard, then that means 150X plus 300Y must be less than or equal to the budget, which is 1,800. Now, I technically noticed that all of these have multiples of 150. So I could actually write X plus 2Y is less than or equal to, well, let's think about this. I believe that's 12, isn't it? 12 150s. 10 150s is 1,500. That's 300 short, and that's 2. Yeah, it's 12. Okay, either of these would be fine. Totally fine. So what that's essentially saying is the number of standard cupboards plus 2 lots of the large cupboards has to be less than or equal to 12. Okay, the cupboards will be fitted along a wall 9 meters long, and the standard cupboards are 90 centimeters long, and the large cupboards are 120. Show this constraint can be modelled by that. Okay, so 9 meters long is 900 centimeters. So the total cupboard lengths has to be 90 lots of X, because they're 90 centimeters long for the little ones, plus 120 Y. I noticed that you can divide by 30 on both sides. So dividing by 30, 90 divided by 30 is 3, 120 divided by 30 is 4, and 900 divided by 30 is 30, and I believe that matches what we need here. So I think I've made my reasoning clear enough. Given also that Y is greater than equal to 2, explain what this constraint means in the context of this question. This means we need to buy at least 2 large cupboards. I don't know, maybe they've got 2 big pieces of lab equipment. This is just me messing around now. Maybe they've got 2 big pieces of lab equipment, and they need at least 2 large cupboards to store them, and then the rest they don't really care about. They just want to maximize it. And the capacity of a large cupboard is 40% greater than the capacity of a standard cupboard. You wish to maximize the total capacity. Show that your objective can be expressed as 5x plus 7y. Okay, so capacity. The total capacity is, well, let's think about that. The capacity of the larger cupboard is 40% greater than the standard cupboard. So the large cupboard is 40% greater than the standard. So x plus, well, if they were the same, then you just have x plus y. But because y contributes more, that's essentially saying that this needs to be increased by 40%. Right? If you increase something by 40%, it's a decimal multiplier of 1.4. Now what I'm going to do is I'm just going to scale this up so that 5c equals 5x plus 1.4 times 5 is 7y. And this 5c is just a new thing to optimize. So I don't know, let's call this like cost prime. It doesn't matter. We want to maximize the capacity, of 5x plus y. Okay, represent your identities graphically on the axis below, indicating the feasible region R. Wow, so we've got to do all of it. Okay, so this is my objective function. So I'm not going to plot that one till the very end. So what have we got? We've got x plus 2y is less than or equal to 12. So if we do the cover up method, cover up 2y, so x is 12, and cover up x, 2y is 12, so that's 6. So we're going to need a line going from 12 to 6. So that's going to look something like that. You'd use a ruler and you do this carefully, and I want that to be less than that, so I don't want the region below, so I'll shade the bit above the line just for giggles, so it's in line with the other questions, but it honestly doesn't matter. It's a graphical representation. You can shade above, you can shade below. It literally doesn't matter as long as you define it. I'm just shading above just so it matches with the other two questions and you guys don't get confused, but do what you want. It literally doesn't matter. So that one's done. Show the... Okay, we've now got to do this one. So let's cover up the y, so 3x equals 30, so x is 10, so let's put a little thing there. Then we cover up the x, 4y is 30, so 2y would be 15, so I want 7.5y. Ooh, that's a bit filth. Okay, so 7.5y is about there, so let's do that properly. So 7.5y is here, and I want that down to 10, like so. And I want this to be less than that, so I don't want the bit above this line. And now I spot that there is an intersection point here. And it looks to be 6,3. But that's just because I've drawn it like that. Let's check to see what's going on. So 6,3. So when x is 6 and y is 3, then if I plug it into the first one, if x is 6 and I double y, is that 12? Yes. And then 3 lots of 6 is 18, plus 4 lots of 3 is 12, that is 20. So yes, this does satisfy the equality of it. So actually, yes, this point of intersection, just in case it's a vertex later on, is 6,3. Okay, now they're both solid lines because they're both less than or equal to, so that's fine. Given, we've missed one almost, given also that y has to be greater than or equal to 2. So that means I have to draw a solid line from 2, like that. And I want everything above, so I'll shade the bit below. Now there's potentially a few vertices here. If there is, this one's a vertex that we're going to need to know. I know that because it's on the line y equals 2, it has a y coordinate of 2, and it crosses this slanted one here, which is this. So if y is 2, I've got 3x plus 4 lots of 2, which is 8, equals to 30. So 3x equals 22, so x is 22 over 3. That's horrible. That's 7 1/3. That's definitely not an integer, I'm afraid. So I'll put that 22 over 3. So really, the next nearest integer is this one here, which is 7,2, just in case we need to maximize things. Okay. Explain what is the capacity of the... No, that's it. I think we've done everything, because the last thing is the capacity function. Okay. So, what is my feasibility region? Well, I'm hoping you can see that it's this thing. It's this weird, funny, was it four-sided? Yeah, I think it's a four-sided. It looks like a triangle, but it's actually got a bit of a deflection going on. It's got a straight line bit here, and it gets deflected down at 6,3, and then it's a straight line. And it's like that. Represent your inequalities graphically on the axis below, indicating clearly the feasible region. This is my feasible region R. And then find the number of standard cupboards and large cupboards that need to be purchased to make your method clear. Okay, so now I'm going to do this thing. So if I want 5x plus 7y to equal something, I could just let x equal to 7. There it is. And y equal to 5. Oh dear. There, and I'll draw a line between the two, looking like that. And now I want to maximize this. So let's think about it. Now you won't be able to do this, but what you can do is you can get your ruler and you can slide it along. Now, which vertex do you think is going to be the last one to hit? Now, oh, thing's moving. It's going to hit that bottom one first, isn't it? So it's... Oh, this is terrible. Okay, look. Okay, what is the gradient of my objective function? Well, if I let 7y equal to minus 5x plus c, and rearrange it a little bit, then y equals negative 5/7 of x plus c. So negative 5/7 is the gradient of this function. So what is the gradient of this top line here? Well, that top line was the 3x plus 4y. So if I look up here, then I've got 4y equals to negative 3x plus 30, divide by 4, so y equals minus 3/4 of x. So this is a gradient of minus 3/4. And the other line was, well, that's just going to be minus half, isn't it? A steeper one. No, it's not so steep. This one's going to be minus a half. So what's going to happen is, because my gradient is minus 5/7, okay, that's fairly steep. So which one is it going to hit first? Can you tell? So I slide it along. It's going to hit that bottom right one first. Can you see? And then it hits the top right one. Can you see how it hits the bottom right one first? The top right one appears to be the last vertex. And you know what? If in doubt, you can always substitute in to check. So we've either got this 6,3 or we've got this 7,2. Remember, we can't have that vertex because it's not an integer solution. So the two ones we need to check are 6,3 and 7,2. So we want to optimize either 5 lots of 6 plus 7 lots of 3, or is it going to be 5 lots of 7 plus 7 lots of 2? Well, 5 lots of 7 plus 7 lots of 2 is 7 lots of 5 plus 7 lots of 2, so that's 7 lots of 7s, that's 49. 5 6s are 30, 7 3s are 21, so this is actually 51. So actually this was the better choice. So it looks like we need 6 standard cupboards and 3 large cupboards. And that will maximise the space. Coolsies. Well, I'm hoping that was interesting and informative. And yeah, I'm hoping it's a fairly easy chapter to understand. I think if you can just graph inequalities and substitute in points and your straight line work is pretty good, then you'll find this chapter pretty easy. Okay, toodaloo, bye.